Hello, ladies and gentlemen, and welcome back. We're going to continue our look, or rather, I should say, we're going to finish off our look at the 2006 Hypatia contest. We're on question number 4 now, and that's the last question on the contest. So, hopefully you've tried the contest, download a copy, tried it for yourself, or at least tried this question. It should prove to be the hardest question on the Hypatia contest. Let's have a look. Alright, so question number 4. The abundancy index, IN, of a positive integer is, IN is sigma of n over n. Oh, look, another function. Where sigma is the sum of all of the divisors of n, including 1 and n itself. Okay. For example, I have 12. Well, here are all the factors of 12. 1 plus 2 plus 3 plus 4 plus 6 plus 12. Divided by 12 itself, and we get 7 over 3. Is that true? 6 and another 6 is 12, with another 12 is 24, and 7, so 28 over 12. Yeah, they both have a factor of 4. Okay, I buy that. This abundancy index is possibly not new to all of you out there. For example, if you know what a perfect number is, like 6 or 28, its abundancy index will be exactly 2, and those are very special numbers that do that. A part. So we got 4 parts here. A part, prove that I of p is less than or equal to 3 over 2 for every prime number p. Now, if I wasn't already thinking it, and I am because I've seen these sort of adding up the factors, adding up the greatest common divisors types of functions before, if I wasn't already thinking it, the fact that we're talking about a prime number makes me think of unique factorization into primes. Okay, I'm going to guess already that I of p times q, when they're both primes, for example, is going to be I of p times I of q. It's just going to split that way. We might have to prove that, maybe that we'll be told that, or maybe this is irrelevant, but that's already what I'm thinking, and I would bet good money we have to do that. Anyway, we're just talking about a prime here, p, for every prime number p, that's fine. As I occasionally do on question 4 on the Galois and Hypatia, and I do encourage this, I'm going to read everything before I do the question, just because they've introduced a brand new concept. In theory, I mean, if this was a well-known concept, they wouldn't feel the need to define it. So they've introduced this brand new concept. They're going to ease me into it, is how it usually works, and then we're going to slowly do some more specific examples to build up a general theory to answer D. That's usually how these go. So I want to know where I should be should be headed with my theory, what I should be thinking about. So I'm going to read it all. So prove I of p is less than or equal to 3 halves for every prime p. For every odd prime p, number p and all positive integers k, prove that I of p to the k is less than 2. I think maybe I can get a formula for that. Maybe. If p and q are different primes, determine I of p squared and I of q squared and I of p squared q, and prove that I of p squared I of q is equal to I of p squared q. It's something that I called a little while ago. And D, determine with justification, because we're supposed to be justifying everything, but determine with justification the smallest odd positive integer n, such that I of n is greater than 2. Okay. So, odd integer, I'm going to guess I'll split it with odd primes, so no factors of 2. Anyway. I think maybe from B getting a formula for p to the k, probably in terms of p and k, should do the trick. And then in C part, I'm going to prove that you can break up I in terms of prime factors, and that should give me a bit of a hand for D. That's just my general thought about this. So I'm going to do sort of A and B together. I think I'm at least going to try. Okay, I'm going to investigate not I of p right away, but I'm going to take a look at I of p to the k. If this doesn't go anywhere, well, you know, if I'm running out of time, I'll just do A, because I think I can do A pretty quickly. So this is all the sum of all the factors, but since they're factors of p to the k, it's just going to be powers of p being added up. All the way up to, we include the number itself, we divide by p to the k. Alright, so I can rewrite this if I wanted to, break it up not as a fraction, but or sorry, not as a single fraction, but as a series of fractions. And then the p to the k over, so we'll get 1 over p, and then we'll get plus 1. So that's certainly something, but it doesn't exactly tell me anything about 2. But whether or not we break it up this way or break it up this way, I think we can see we have a geometric sequence being added up. So it's a geometric series. So this fellow right here is a geometric sequence. And when you have a sequence like that, when you have a followed by ar and then ar squared and so on, if I want to add them all up to a certain point, then there's a formula for that, and it's a8r to the k minus a over r minus 1, I think. Anyway, what we can do here is we can say a is 1. Really, the easiest way to, I think, do this is just multiply the top and bottom by 1 minus p. Or, sorry, p minus 1. Over p to the k, and so we'll get minus 1, we'll get p to the k plus 1. So I knew my formula was slightly off. And then we'll get p minus 1. Everything else cancels. This is what's called a telescoping sequence, or telescoping series, I guess. But here's my formula. So this is my formula for I of p to the k. Okay. Where can we go from here? I want to write that a little nicer. So I want to show that this is... So I agree with this. I suppose I could bring the k in, like the p to the k in like that. We'll have p to the k plus 1 minus p to the k. So this should be our formula. I'm just going to quickly test it out. If p is equal to 2 and k is equal to 2, we get 1 plus 2 plus 4 all over 4. So 7 over 4. And what would my formula say? It would say 8 minus 1 over 8 minus 4, which is 7 over 4. So yeah, that works. Okay. Now what do we do? So for A, we have k is equal to 1. So I of p to the 1 is just p squared minus 1 over p squared minus p. Well, that really becomes p plus 1 over p. Not particularly interesting, but I want to show that that's less than or equal to 3 over 2. 1 plus 1 over p. And then this gets smaller as p gets bigger. P is always greater than or equal to 2 because it's a prime, so I of p equals 1 plus 1 over p, which is less than 1 plus 1 over 2, which is equal to 3/2. Okay. So that proved A. Didn't exactly use my formula, but then again, A was supposed to be before we developed this formula. Now for B, I want to show how we don't have 2 here. For B, we know I of p to the k is p to the k plus 1 minus 1 over p to the k plus 1 minus p to the k. And I need to show that this is less than 2. Well, if that's true, then what have we got? Multiply through. P to the k plus 1 minus 1 has got to be less than 2p to the k plus 1 minus 2p to the k. Subtract p to the k. And I think we needed odd, didn't we? Yeah, for every odd prime. So this is p to the k, p to the p minus 2. So this guy here, always positive. And p is greater than or equal to 3. So this is always positive. And so this is true. Okay. You'd also start with this result and work backwards, but we've shown that p to the k is less than 2. Okay, not bad, and got my formula here for p to the k. Okay, so C part was determine these. Well, I got formulas for these. I don't have a formula for this one. Now, I could either write out a formula for this one and prove this, or what I could do is prove, I would say, the general result. So the general result, I'm going to start another page. For C, I'll prove the stronger result. That if A and B are such that the GCD of A and B is equal to 1, then I of A, I of B is equal to I of AB. Okay, I'm fairly certain this is true. The question is just, how do we prove this? What do we do? So I of A, I of B, well, that's just sigma of A, sigma of B, AB. And we want to show that that's sigma of AB over AB. It suffices to show sigma of A, sigma of B is equal to sigma of AB. Okay. So, how do we do that? And of course, if I fail in doing this, or if I get stuck and I think I'm going to run out of time, I can just work out. I mean, I of p squared plus q, or I of p squared q. It's going to have factors of 1, p, q, p squared q, pq, and I'm missing 1 q, pq, p squared q. It's only going to have 6 factors. So it won't be that hard to add it up and undo everything. And the idea is that we're going to factor things out. So sigma A equals the sum of all the divisors. So I'll show you an example of what I'm planning on doing. So if I had, say, 1 plus q plus pq plus p squared q, and then p squared q. I could rewrite this. I could factor out And hey, this is the sum. This is sigma of p squared. This is the sigma of q. But this one over here is the sigma of p squared q. So this is how you would do the C part normally. I want to prove the more general result because I'm fairly certain it's going to be useful for D part. That's determined with justification. I want to start making an odd positive integer by unique factorizing it. And I need to show that the result still works. So, let D be a factor of AB. Then, actually, you know what? I'm going to, because I don't want to have to set this up, I think I'm actually going to instead prove the easier result. So let's ignore this. I'm going to do a slightly easier version of this just because I don't want to be messing around with common divisors and things like that. If n is p1 e to the 1, p2 e to the 2, yada yada yada, then I of n is I of p1 e to the 1, I of p2 e to the 2, and so on. So this would still follow from the other thing I'm trying to prove, and this actually proves the other thing that I'm trying to prove, I believe. Yeah, this would prove the other thing, the thing I originally said I wanted to prove. So they're equivalent statements. I just think working with the primes is going to be a lot easier. So, as I already remarked, it suffices to show sigma of n is sigma of p to the 1 e to the 1, sigma of p to 2 e to the 2, sigma of pk e to the k. Okay, so it suffices to do that. Well, so sigma p1 e to the 1 all the way up to sigma pk e to the k. That's really just equal to 1 plus p1 squared, And then we're also going to have the p2s, and then all the way up to 1 plus pk e to the k. Okay. So when I multiply these out, I'm going to FOIL it all out. It's going to be the sum of all products of the form p1, I don't know, a to the 1, p2, a to the 2, pk, a to the k. With 0 less than or equal to a1, less than or equal to e1, 0 less than or equal to a2, less than or equal to e2, yada yada yada, 0 less than or equal to ak, less than or equal to ek. So it's going to be the sum of all products of the form, each one appearing exactly once. As if you're of the form p1 e to the 1, you have to have used the p1, not p1 e to the 1, p1 a to the 1, you have to use the p1 a to the 1 factor here. You'd have to use the p2 a to the p2 to the a2 factor in the middle, and so on. I don't think that really needs to be explained. The only thing I need to explain is these guys happen to be all the factors of n. notice that if D divides N, which is P1 e to the 1, Pk e to the k, then D has to be equal to something of this form. And so that shows me every divisor of n is in that sum. And now let's show that every term in the sum is a divisor of n. And also, we know that anything of the form like this is a divisor of n. Okay, so it took us a moment there, but we proved sort of the grand result. We showed that the sums, the product is going to be something like this. Well, it turns out that happens to be the sum of all the divisors of n. So it turns out the sigma of n is the sum of all these products. And we've calculated this in two different ways. So sigma of n is sigma of p1 to the e1, and then all the way up to sigma pk to the ek. Now, just as a word to people out there, you might be thinking, well, you sort of skirted around the fact that you've been using the fact that they're primes, and that's true. If I wrote sigma of 12, for example, is not sigma of 6 times sigma of 2. Let's look at why. This would be 1 plus 2 plus 3 plus 6, and this one here would be 1 plus 2. You're going to get extra factors that you didn't plan here. So for example, we're going to get 3 times 2 is 6, but we're also going to get 1 times 6 is 6. So you're going to get duplicate factors here, and that's the problem. Because 6 is 2 times 3. Well, are you using the 3 in the 1 plus 2 plus 3 plus 6 and the 2 from 1 plus 2? Or are you just using the 2 times 3 that's in it? But when you have that's part of the 6 in the 1 plus 2 plus 3 plus 6. But when you have a product of primes and you're looking at, okay, where did this p squared come from? Well, it has to come from the p squared in the sum of 1 plus p squared plus. So the unique factorization into primes really saves us there. And you can clarify it if you want, but we're just gonna jump around this question here. So we've shown that, and from there, I of n is I of p1 e to the 1 pk e to the k. Okay, and this allows us to show C. So I know that I of p squared is equal to p squared minus 1 over p squared minus, p cubed minus 1 over p cubed minus p squared. Well, that's one of the things they asked me to show. They asked me to show I of q is q squared minus 1 over q squared minus q. And now I can say, well, I of p squared q is the product of these two. And there are other ways you could have written it out, but I like using this method. Okay, I've calculated them all. Okay. And I use the fact that since p and q are different prime numbers, that this result that I've just proven actually works. And you can do it the other way. You can do it actually listing out the factors of p squared and q. If you want to do it that way, that's fine. I'm just trying to bundle some of these parts together because I have a feeling this is a long question. So we sort of did A and B together, and we're doing C and now D together. So we just did C. The way they originally had C, they wanted us to realize, oh, it splits based on prime factorization. Now I can do D. That's my guess. So now determine with justification the smallest odd positive integer n, such that I of n is greater than 2. Okay. So, we know from B that I of pk is always less than 2. So n must not be a power of a prime. Okay, so it's not a power of a prime, that's fine. Can it be something like, it's got to be odd, so can it be something like 2 powers of primes? Could I have I of p to the k, q to the m? Okay. Not seeing anywhere to go with this. There's nothing that immediately says this can't work, because all I know is that these both have to be less than 2. And then there's the question of smallest. Because maybe I can do this. Maybe 3 to the 300 and 7 to the 2000 works. But maybe by introducing like 3 times 5 times 7 squared times 11, introducing some more primes will bring this number down significantly. So I think rather than just jumping in and looking at does two powers, two different primes work, maybe I should start investigating the exponents for a moment. One thing I would like to note before we move on, since n is odd, n equals p1 e to the 1, pk e to the k, and each p1, p2, all the way up to pk are odd. So no 2's in this product. Maybe the exponents are 2's, but certainly not the primes. And I think this will help us out. Now, since everything can be boiled down in terms of these pk's, how do these two relate? My gut instinct tells me I've got a relationship like this. But it must go up a very small amount each time, otherwise this guy would eventually, because he would eventually become greater than 2. So it must go up a very, very tiny amount. But let's look. Let's look and compare, and let's learn and understand. I of p to the k is p to the k plus 1 minus 1 over p to the k plus 1 minus p to the k. I of p to the k plus 1 is p to the k plus 2 minus 1, p to the k plus 2 minus p to the k plus 1. Now the bottom, so if I multiply by p over p, this is p to the k plus 2 minus p, and this is p to the k plus 2 minus p to the k plus 1. So we do get bigger. Is there a measurable way how much we get bigger? In fact, the difference there is, so those two cancel out, so it's something over p to the k plus 2 over p to the k plus 1. It's p minus 1 on top. But then I can factor out that p minus 1, and it's just going to be 1 over p to the k plus 1. Which actually I think would have followed from I did have it written out as I erased it, but I did have it written out like this, and so suddenly, yeah, that result makes sense. So maybe getting this formula wasn't exactly the best way to go, but that's what I did. And that's okay. No use in saying, oh, geez, I wish I'd done it better. Yeah, you're writing a contest. You do what you can. You get the results that you can. Anyway, so we know the difference in those, and that's good in some way. But higher powers of k means higher values of I of p to the k plus 1, or higher values of I of p to the k. Does this actually help us with our primes, though? With finding an n? I'm not seeing a particular thing that I might want to do. Maybe if I rearrange my formula a bit. So instead of multiplying by so I'll have p to the k plus 1 minus 1 over p minus 1 all over p to the k. I think that's a more sensible way to write it, because now I can say I of p to the k, q to the m. I can quite quickly put those guys down there on the bottom. K plus 1 minus 1 over p minus 1, q to the m plus 1 minus 1 over q minus 1. So just because I find them doesn't mean I can get very, very small. It doesn't mean I can't get smaller. So, well, let's finish this off. So I want this to be bigger than 2. So 2p to the k, q to the m has got to be less than, and we'll multiply through by p minus 1, q minus 1 as well, has got to be less than or equal to p to the k plus 1 minus 1 times qm plus 1 minus 1. Okay, a lot to unpack there. 2p to the k, q to the m. This is pq minus p minus q plus 1. And this is pk to the plus 1, qm plus 1, minus pk plus 1, minus qm plus 1, plus 1. Okay. Lots of stuff going on there. I don't know what would be the best thing to do here. I also don't know which primes are best, if there are even are primes. Like I did some examples that said 3, 5, maybe 7. But how do I know that just having these two, like 101 and maybe, gosh, what's another prime? 191. Maybe those two work, and they just maybe 3 to the 300 works, and 5 to the 700. But maybe those aren't the best. Maybe just 101 and 191 work. So in the absence, I could probably expand this out, but I don't think it's going to tell me a whole lot. I kind of get the sense that maybe there is, maybe there are primes that are good. What do I want to do here? I think I'm going to erase this. I'll come back to it. I don't want to, but it seems like it did. I don't have enough direction. The K's, the M's. I mean, yes, I of p to the k gets bigger as k gets bigger. That doesn't particularly help me. I know I can order my primes, so if P is less than K, or sorry, if P is less than Q, how do I want to get rid of the M. How do I of P to the K and I of Q to the K compare? This should be straightforward, and it should be this one is smaller, maybe? No, I think this one, I think it should be bigger, which would actually be quite helpful, because then it means we want to shoot for the 3s and the 5s. I think, well, hold on, let's actually just work it out. I don't think this formula is the thing I want to go with. I think I want to do... So this guy here is 1 plus 1 over P plus 1... This is a much better formula. I should have been using this all along. It's not closed form, certainly, but each of these guys, because P is smaller than Q, each of these is bigger than his corresponding Q counterpart. So, yeah, we should have... It's definitely greater there. And that's because this implies that 1 over P... Well, it implies... I'll say it implies P to the A is less than Q to the A, and that means that 1 over P to the A is greater than 1 over Q to the A. Okay, so it wasn't much promise when I looked at IP to the K versus IP to the K plus 1. That didn't particularly help me, I don't think. But this definitely shows that, so for example, if I of 5 to the 20 and I of 7 to the, 4 is greater than 2. If that works, if that satisfies the thing I want, then I know for a fact that this has got to work even better. And I can even put, I can make this 7 and 101. These have got to be even better. So they will also definitely be greater than 2. Okay. So that, at last, has narrowed something down for me. If I think that I can do it with 2 powers, then I should be able to do it with P equals 3 and Q equals 5. Great. Okay, now let's see what that would do. And then, if I can get an answer there, I'll see, can I do better with 3 powers, or with 3 primes. And so from there, and I think eventually there'll be some sort of happy medium area there, maybe around 4 primes or something like that. Who knows? Okay. So, if n equals P to the K, Q to the M has I of n greater than 2, then 3 to the K, 5 to the M also works. So let's just see when does 3 to the K, 5 to the M work, if ever. So I of 3 to the K, I of 5 to the M. This time I'm going to use the closed form. And we will do 5 to the M plus 1 minus 1 over 5 to the M plus 1 minus 5 to the M. But that's 2, 3 to the K on bottom, 3 to the K plus 1 minus 1 on top. And then 4, 5 to the M, 5 to the M plus 1 minus 1. So we've got 1 over 8 times 3 to the K, 5 to the M. I'm going to call 3 to the K, 5 to the M equal to N. So we've got that, and then we've got 3 to the k plus 1 minus 1, 5 to the m plus 1 minus 1 there. And I want this to be greater than 2, so we want 3k plus 1 minus 1, 5m plus 1 minus 1 be greater than 16n. Okay, well that's going to be, nope, can't combine them that way. We're going to have 3k plus 1, 5m plus 1, minus 3k plus 1, minus 5m plus 1 has got to be greater than 16n. And again, I just can't quite make k and m work here. So am I missing something? It's like, surely a 3 and a 5 should probably do the trick at some point. I just can't quite tell. And I know that these questions, like this question is based off of things like the concept of perfect numbers. Abundancy is how you define perfect numbers. And I know perfect numbers are not the easiest thing to work with. But man, either I have got the wrong setup or this is just a hard question. I probably have the wrong setup. I know my formula earlier wasn't the nicest thing to work with. Can I assume something like 3 is k? Because that would be nice. Yeah, I think not 3 is k, but 3 is the one that goes with the higher power. We can assume k is greater than or equal to m. Why would that work? Well, if I had p to the k, I of q to the m, I know this is less than I of p to the m, which is, no, can I say that? I think I can assume that the square, like not the square, but the bigger power has to go with the smaller number. Question is why? So I, p to the k, that would have to be, so if I had that one and if I had this one, and I want to compare it to if I had it the other way around. So he's less than that, he's less than that. He's less than that, and he's less than that. Not immediately clear. Maybe I can't. Maybe I can't do that. Well, let's actually try some. The theory seems to be failing me. Let's try some numbers. So, 15, that's going to be 1 plus 3 plus 5 plus 15 is 24 over 15. .6, not helpful. What if I did 45? That'd be 1 plus 3 plus 5 plus 9 plus 15 plus 45. And then divide that. So it's 78 over 45. 1.7. So it's getting higher. Now compare that to 75. So 1 plus 3 plus 5 plus 15 plus 25 plus 75. That's 124 over 75. And that is less than I of 45. So that does sort of support the bigger exponent's got to go on the smaller primes theory. What shall we do? My formula has not been the most helpful. So I'm going to take a look at this. This is also whatchamacallit? This is also a geometric sequence. Geometric series. And I know it's less than I of p to the k plus 1, but this is actually has a common ratio of 1 over p, and so this should be less than the infinite sum. Just keep going. And the infinite sum here has 1 over 1 minus 1 over p. The infinite sum has a formula, which in this case is equal to p 1 over p minus 1 over p. So this is p over p minus 1. Which of course is bigger than 1, but will never be more than 2. And this would be another way to prove b, and I like this a lot better because now I've shown that there's sort of a limit to what I of 3 to the k can be, and I of 5 to the k, and that sort of stuff. And I think this might be the better way to do it. So maybe question 4 not so bad. I was an idiot. Well, not an idiot, but I chose the wrong formula, and that seems to have made all the difference here. Because I have been struggling, whereas I think I of 3 to the k now has to be less than 3 over 3 minus 1, so it has to be less than 3 over 2. I of 5 to the m has to be less than 5 over 4, and the product of these two has got to be less than 15 over 8, which will always be less than 2. Okay, can't do it with 2 powers. So, n can't have 2 primes for its factor. So this is working out so much better. Okay, so I can't have 2 primes for its factors. How about 3? How about 3 prime factors? So that would be something like, at best we would have I of 3 to the k, I of 5 to the m, and I of 7 to the p. I don't know. But that's going to have to be less than 3 over 2, 5 over 4, 7 over 6. And these are the best ones. No need talking about an 11 here. So that's 105 over 12 times 4, so 48. And that finally is greater than 2. Okay? Does it mean I have to use 3 powers? No, because if I had 4 powers might work and be less, which is something I was saying earlier. But I know I didn't need to check using only 2 prime powers, and n being 3 to the k, 5 to the m. But now I do have to sit and check these ones here. Okay. So, how about, well, let's just start working these out. 3, 5, 7, so this would just be 1s everywhere, is 105. 3 squared, 5 to the 1, 7 to the 1. 105 isn't exactly this one, but we'll work a couple out. It's going to have to be... So we'll work a couple of these out and get a sense of how are our numbers actually doing. Now, I of 3 is... what did we say that was? 3 plus 1 over 3, so it's 4/3. I of 5 is going to be 6/5. I of 7 is going to be 8/7. Okay. I of 3 squared is going to be 3 squared minus, so 8 over 6, which is 4/3 again. That seems weird. 5 squared, so that'd be 25 minus 1, so that's 24 over 25 minus 5, so that's 24 over 20, or 6 over 5. I feel like I'm doing something wrong, because I keep getting the same values. And I know that's not possible. So was my original formula wrong? Oh no, it's because I'm squaring and not cubing. Additionally, I could just add a 9th here. I think I'll just do that. So I of 9 is 13 over 9. I of 25 is going to be add 25 to this. So that's 31 over 25. And I of 49 will be 57 over 49. Okay, so let's take some products here. So this is 4 over 3, 6 over 5, 8 over 7. There's no way that's happening, but we'll just double check. 4 times 6 times 8, 192 over 105. So no, that one's no good. It might be that none of these are no good, although look, it's pretty close. Pretty close. So we'll do 13 over 9, 6 over 5, 8 over 7. 13 times 6 times 8. We had 624, and then that's over 315. That is not far off either. I'm betting one of these two might do it, actually. In which case, then we're almost done. We just need to show that there's not one with 4 or 5 primes that is less. So this is 4 over 3, 31 over 25, and then 8 over 7. And that's going to be over 525. And then we've got 31 times 4 times 8. 992. No, that's worse. We needed something over 1050. So, let's try 57 and 49, but I think that's not gonna go so well. So that'll be over 735. And then what's on top? 4 times 6 times 57. 1368. That's no es bueno. Because we'd need 1470. And that's not what we've got here. So it looks like the best thing for us would be to use 3 cubed. So we'll try it with 3 cubed, but maybe we'll have to go with 2 squares. So this will be 6 over 5, 8 over 7, and then we need a 27 plus 9 plus 3 plus 1, all over 27, so 40 over 27. And then 27 times 5 times 7 is 945. And 40 times 6 times 8 is 1920. And that, sadly, is... Oh, it is. It works. Okay, good, good, good. So that one is greater than 2. And that will be smaller than any 5 to the 3 or 7 to the 3. And actually, it'll be... so it's smaller than any of our other candidates, which would be something like this. Or 3 squared, 5 to the 1, 7 squared. So this guy really is the smallest one that works with powers of 3. Or not powers of 3, but with 3 primes. I keep mixing up primes and powers as I'm talking, and I imagine that's probably confusing for you guys out there. So this is the smallest with 3 primes. What about with 4 primes? Now obviously 4 primes has the potential, but the smallest thing with 4 primes would be something like this. And that is going to be more than this, because 11 is more than 9. So we don't even need to bother. We don't need to bother with that. So this definitely works, and I just want to mentally double check. We can't do small. We definitely can't do small. We have to have a 3, a 5, and a 7. Do we have 3 squared? So this would be... So this is the smallest thing with 5 as the sum of the exponents. And then these are the ones that have 4 with the sum of the exponents. We could have 3 to the 1, 5 squared, 7 squared, but that's also going to be less. Yeah, this one is the best. So 945 is the smallest such n. Okay. That took a lot longer than I think it should have. Not a bad question per se. If you've seen things, so some things that I did to make it more complicated for myself, which turned out to be bad. I jumped on a formula pretty quickly, and I latched on tight to that one, whereas there was a better formula just with those sums of reciprocals staring at me in the face. So that's something that I did that was not so good. So the lesson you guys might want to take is don't get married to one formula. Other things that I almost made it really hard for myself by trying to do that GCD of so if A and B were relatively prime, then I of AB is I of A times I of B. That almost got me, but I decided to break it up into primes, and I think you'll agree that went much faster. But yeah, D part, I should not have just stuck with that formula because it cleared too many variables, and I did not see the sort of limit, the infinite geometric series that clearly helped us out there, which is really nice. I assume that I have to imagine the formula they use in their solutions. They just go straight for the 1 plus 1 over p plus 1 over p squared and things like that. I don't know if there's a whole lot more to say. It's been an odd Hypatia this time. This question caused me some issues. I know I think I was dragging my feet on a couple of the earlier ones. But yeah, that happens some years, and you just gotta hope it's not the year that you'll write the paper for real, where it's super official. And certainly hope it's not the year you're writing the Euclid for your scholarship. But if that happens, know that there are other people out there who are struggling the exact same year. And yeah, that's it. 2006 Hypatia done. We'll be on to the 2006 Euclid. And so that'll be the next contest, and there'll be more Hypatias and Fermats, other things at the grade 11 level in the future. 2007 Hypatia, of course, will be around eventually. So I will see you guys in those videos, and thank you so much for watching. Thanks for sticking with me through this one, and I'll see you next time.